this video, we will present the quality of services techniques implemented in the InfiNet Wireless units. This video is structured in 3 parts: the need of the quality of services in a data transfer network, the general challenges that the QoS addresses, and the implementation of the QoS mechanisms in InfiNet wireless gears in order to address these issues. Hundreds of megabits per second flowing wirelessly nowadays are common. However, in wired networks, the flows are measured in gigabits per second. If no congestion management feature is available, packets will be dropped, resulting in an increased retransmissions rate. Retransmissions will add extra load to the already congested network, and it will further degrade the performance. Such behavior could be nearly satisfactory for typical internet surfing, social networking, or email exchange. However, there are plenty of applications and services which are sensitive to increased latency and packet loss. Voice over IP, VoIP, video conferencing, IPTV, business-critical apps like CRM and remote desktop are among them. The immediate solution is to increase the throughput of the wireless link, to set up additional wireless links, or to substitute wireless with optical fiber. But such solutions are expensive and sometimes not practically feasible. The second option, and in the majority of the situations the best option, is to implement quality of services techniques. At the basic level, the network quality is evaluated by the loss, delay, and jitter parameters. Loss represents the number of packets that were not received against the total number of packets transmitted. To improve the loss in our network, the QoS mechanisms determine the selective drop in order to ease the congestion when present. Delay represents the amount of time a packet travels between the sending and receiving endpoints. Jitter is the delay variation of the transmitted packets. For example, if one packet requires 100 milliseconds to cross the network, and the following packet requires 125 milliseconds for the same trip, the delay variation will be 25 milliseconds. To overcome such situations, each endpoint uses a jitter buffer to smooth the delay variations in case of voice over IP, VoIP, or video over IP traffic. The first task for the QoS is to differentiate between the traffic flows. Let's consider the differentiated services which can serve the QoS packet classification purposes by using a 6 bits differentiated service code point in the IP header of the packet, part of the 8 bits DS field. The DS and ECN, for congestion notification, fields replace the outdated type of service. A packet with DSCP priority 48 is illustrated in the picture. The marked packet arrives to the InfiNet unit, and the next task of the QoS is to map the DSCP value to the corresponding mint priority, which in our case is mint prio 1. The proprietary Mint protocol assigns a priority that will be used to transfer through the whole Mint network. Another traffic filtering method is based on the class of service priority values, or 802.1p priorities. COS is a 3 bits field in the header of the Ethernet frame when the 802.1q VLAN tagging is in use. The second example shows a packet marked with COS priority 3. The COS priority is mapped to Mint priority 9 by the QM module inside the InfiNet unit. The conversion table between Mint priorities and 802.1p/TOS/DSCP priorities can be found in the product documentation. Additional traffic selection criteria are available for the InfiNet wireless units, including IP or MAC addresses, VLAN tags, MPLS EXP values, TCP or UDP ports, and custom PCAP expressions. The next task of the QoS is the traffic queuing and packet scheduling. The scheduling techniques determine when a packet shall exit a device based on its assigned priority. In the picture, we can see how packets with different priorities are sent in different queues. Since Mint priority 1 packets carrying voice services are more important, they will take precedence in emptying the queue. For this reason, it can be noticed that the business priority queue is filled in while waiting for the voice traffic to be transferred. The strict priority queuing is used in this example. The QM module supports strict priority queuing and weighted fair queuing scheduling algorithms. In case of strict priority queuing, packets within lower priority queue are not processed if the higher priority queue is not empty. In case of weighted fair queuing, weights are used for every queue of an interface, which allows for different queues to have different service shares depending on the weight value. Another task for the QoS is traffic shaping, which retains the excess packets in a queue, buffering the delayed packets, and schedules the excess for later transmission. The result is a smooth output packet rate. We can see in the animation how packets arrive to the InfiNet unit at random speeds, generating a fluctuating throughput. By contrast, the packets exit the unit in a uniform manner, ensuring a constant desired throughput. Now, let's see how the QoS can be implemented step by step using InfiNet wireless gears. Auto QoS features are implemented by the InfiNet units, which can automatically prioritize the following traffic types: RTP, ICMP, 802.1p marked, TOS, and packets with TCP ACK. The scope of the first scenario is to show the functionality of the Auto QoS feature. For this purpose, the client PC will be generating RTP traffic over a point-to-point InfiNet wireless link in order to reach server. Let's see how the slave unit treats the RTP traffic. The first step is to check the Auto QoS setting for RTP traffic. Let's go to the basic settings in the QoS options section. As it can be noticed, the automatic prioritization for RTP packets is enabled. The RTP 802.1p tags and ICMP options are by default enabled. In order to see the effect of this configuration, let's check the general statistics for the RF interface. At this point, the voice mode is off, meaning that no RTP traffic is detected by the unit. We can also see in the Wireshark trace that traffic is sent over the link. I'll next generate RTP traffic from the client PC. We will be able to see this way how the voice mode status changes automatically to on, reacting to the incoming RTP traffic, and that the RTP packets are captured also by the Wireshark trace. Additionally, we can check the QoS statistics for the RF interface in order to see the priority queues incrementing. Let's reset the counters. We can observe that traffic is incrementing in Q24 with mint priority 2 as expected. For full mapping of the mint priorities, the product documentation can be consulted. Let's consider now a different scenario. We'll assume that a CRM business platform requires 7 megabits per second guaranteed out of a total available bandwidth of 10 per second in order to ensure the desired quality of the CRM services. Without any traffic prioritization, and due to the specific of the FTP protocol, the data traffic between the FTP server and the FTP client will increase so much that the CRM platform will get less and less bandwidth. In order to address this issue, QoS policies will be applied for each type of traffic. The first step is the traffic selection. The FTP traffic will be treated as best effort, and it will be mapped by the QM module to mint priority 15. The CRM traffic will be marked with DSCP priority 16 and further mapped to mint priority 10. The last step will imply the definition of the bandwidth allocation policies. 7 megabits per second will be guaranteed for the CRM business application and 3 megabits per second for the FTP traffic. In case that only one service is running at a time, the whole bandwidth will be allocated to it. Let's see how this is done using InfiNet wireless units. In the Basic Settings page, choose the Extra Commands section. In order to dynamically allocate bandwidth between different services, we have to define a service class and specify the maximum bandwidth available. Let's create Class 1 with the maximum bandwidth of 10 megabits per second, as in the case of our specific scenario. Next, we have to define the QM channels. The Mint QoS Manager uses logical queues called QM channels for implementing the QoS policies to different traffic types. Let's add channel 1 and create a filtering rule based on the DSCP priority. This way, all the incoming CRM traffic marked with DSCP priority 16 will be bound to channel 1. In the same manner, I'll add channel 2 in order to use it for the FTP traffic. The last step is to specify the mint priorities and the bandwidth allocation policy. Let's map channel 1 with mint priority 10 and specify that it should use 70% of the available bandwidth in case of concurrent traffic with the FTP server. Otherwise, it can make use of all the available bandwidth. For channel 2, I won't specify any priority, meaning that the FTP traffic will be treated as best effort and map to Mint Priority 15. 30% of the bandwidth will be guaranteed, otherwise all the bandwidth can be used. To be noted here that the seal value can be configured as less than 100%. The configuration is finished, so let's save it and test it. We'll check the throughput variations at the CRM client. Initially, I'll generate only CRM traffic. We can see in this case that the full 10 megabits per second bandwidth is in use by the CRM business application. Let's check with Wireshark that the DSCP is indeed set to 16. In the IP header, we can see that the packets are marked with DSCP 0 × 10 in hexa, which translates into a value of 16 in the decimal system. Now, I'll start generating also FTP traffic. It can be immediately observed how the bandwidth used by the CRM service has decreased to the guaranteed 7 megabits per second following the QoS policies I previously defined. It is therefore demonstrated that the CRM traffic has a constant 7 megabits per second guaranteed bandwidth in order to sustain the desired quality. Also, to be noted that if any of the services will be transferred with less capacity compared to the guaranteed bandwidth, all the remaining bandwidth will be allocated to the other service. The last thing to check is if the Mint priorities are assigned according to the configuration settings that were performed. I'll open the QoS statistics and reset the counters for this. As it can be seen, the queues corresponding to Mint Priority 10 and Mint Priority 15 are incrementing as expected, one for the CRM traffic and the other for the FTP traffic.